Hey everyone, Sakani here. Today we're going to be taking a look at how we can apply this special theorem into problems such as these. So let's actually dive right into it. This theorem states that integration 0 to a, where a is a constant of f of x dx, is equal to integration 0 to a of f of a minus x dx. And yes, this is actually a real theorem and we can apply it to different scenarios. It is true you can apply this theorem to any integral out there. It might not always be the best practice because depending on the integral, it might create a more complex integral or it could create a more simpler integral. How do you know when to use this formula? Well, I like to use this formula whenever we're talking about trig identities or some like trigonometric functions, sine, cos, tan, cot, you name it. So that is why our first question here is related to trigonometric identities, and let's actually see how helpful this can be. So I'm actually going to set this integral, integration 0 to pi over 2 of sine x over sine x plus cos x dx. I'm actually going to set that equal to I. Alright, so I is equal to this integral, and now I'm actually going to straight away apply this theorem. I is equal to integration of 0 to pi over 2. In this case, pi over 2 is going to be a. So we have sine of pi over 2 minus x over sine pi over 2 minus x plus cos pi over 2 minus x dx. And basically how I did that is that a we know is pi over 2, so then I replace everywhere where there was an x with pi over 2 minus x according to that formula. So now over here, we should know a little bit of our trig identities. For example, I can simplify sine pi over 2 minus x. That is just equal to cos x. And cos pi over 2 minus x is equal to positive sine x dx. Now you might be thinking, wait a second, if we compare this to our original problem over here, we just see that the sine became a cos and the cos became a sine. How is this going to help us? This is going to help us because I'm going to take this and I'm going to add them. So I'm going to add I is equal to this integration and I is equal to this integration. So the left side is going to be I plus I, which is 2I. And the right side is going to be 0 to pi over 2, this integral, so sine x over sine x plus cos x dx, plus integration 0 to pi over 2 of cos x plus sine x dx. And now we can definitely simplify this. So the left side is going to stay the same. Our bounds are also going to be the same, but now we just add these together. So we get sine x plus cos x, and the denominator, same denominator, we're just going to keep it as it is, sine x plus cos x. And now I think you could see that we can definitely simplify this. We have sine x plus cos x over sine x plus cos x, easy. That is just going to be equal to 1 dx. And we know integration of 1 dx, pretty simple to solve. So we are just going to have 2I is equal to x, and then bounds are going to stay the same. And from here, we get 2I is equal to pi over 2. Therefore, I is equal to pi over 4. So the main takeaway over here is that we needed to use this formula over here in order to simplify it to this. And it was also crucial that we set the original problem to I, so that when we added this function and this function, we were able to get this over here, and that was just 1. Alright, on to our second problem. We have integration 0 to pi over 2 log tan x dx, and I think you can start to see a pattern. All our questions have a trigonometric function. Last question, it was sine x and cos x. This question is just tan x. So I think let's just go ahead and apply this formula, being sure to first set I equal to 0 pi over 2 log tan x dx. And applying this formula now, we get I is equal to integration 0 to pi over 2. Pi over 2 is once again our a value, keeping that in mind. So we are left with a log tan pi over 2 minus x dx. And let's make that 2 a bit clearer. Pi over 2 minus x dx. Using our trigonometric identities, we know that tan pi over 2 minus x is equal to cot x. So I'm going to rewrite this as just cot x dx. And I'm going to take a pause over here. Our first integral was this integral right over here. And this is our second integral over here. We're going to do the same exact thing as before. We're going to add these two together. So we're going to add the left side and we're going to add the right side. So if we add 1 and 2, that is going to be 2i is equal to integration pi over 2 of log of tan x dx plus integration 0 to pi over 2 of log cot x dx. Now over here, we can start to add them. So we get 2i is equal to integration pi over 2 of log tan x plus log of cot x, and then this whole thing is dx. Now we do need our properties of logs. I know that log a plus log b is equal to log a times b, so I'm going to apply that property over here. So this essentially is equal to log of tan x times cot x dx. And tan x times cot x, well, that is just 1. 2i is equal to integration 0 to pi over 2, and we know that log 1 is just 0 dx. I know that this is equal to 0, so that has to mean that if I take 2 to the other side, I is also going to be equal to 0. All right, on to our third problem now. Integration 0 to pi over 2 to log sine x minus log of sine 2x dx. Now, what many of you might go ahead and do is that you might go ahead and try to apply this formula directly, and that is actually going to be an incorrect way. By incorrect, I mean that you'll get to a point where you're not really sure what to do afterwards because you can't apply u substitution or integration by parts or any other method. But let's actually try that to see why it is wrong. So I'm going to label this wrong. This is the wrong way to do it. And we're going to have integration pi over 2 of 2 log sine of pi over 2 minus x minus log sine of 2 pi over 2 minus x, and finally we have dx at the end. Now let's simplify this. Expanding this, we are left with pi minus 2x dx, and I think we see where the problem arises. We don't really have a trigonometric formula to simplify pi minus 2x. We do have a formula to simplify pi minus x, but we don't know what to do with pi minus 2x. So sure, you could work around it, but honestly that would be a very lengthy process when in reality we first need to simplify this integral. I see a lot of logs, and using the properties of logs we could simplify this integral before applying this method. Going back to simplifying, let us make this integral equal to I. Alright, that's equal to I. Now I know that sine 2x is equal to 2 sine x cos x, so I'm going to rewrite it as. So that is the change that I made over here. Now I'm aware that I could simplify this a lot because I know that log a times b is equal to log a plus log b. So I'm going to leave this the same as it is, 2 log sine x minus, and I'm just going to go ahead and simplify it. So when I simplify it, I'm going to get minus log 2 plus log of sine x, and then those parentheses, plus log of cos x, and then we have another parentheses dx. And this is equivalent of this by applying those logarithmic rules, and we have to distribute that minus. Alright, and we can start to see that this and this, they can be simplified to just a log sine x. So I've written it a bit neater. I have simplified this whole entire expression, and now we are left with this. Instead of applying this formula directly, I do want to separate it into its own little integrals because I know this is a constant. I can take that constant out. So I'm actually going to separate it into 3 different integrals. So once we have separated this into its integrals, now we are ready to apply that formula. So I'm going to set I is equal to 0 to pi log of sine pi over 2 minus x dx. And this integral, I'm going to take that log 2 out because it is a constant. We're left with 1 dx. And finally, I'm going to apply the formula to log of cos x, marking it as log of cos pi over 2 minus x dx. Now from over here, let's start simplifying. We know this is equal to cos x, and we know this is equal to sin x. But as you can see, we have this and we have this. We didn't really simplify anything, but I noticed that from the back over here, we had this integral, and now we have this integral from cos x. So I'm actually going to rewrite this, and I'm going to go back 2 steps to over here. And I'm going to rewrite this in terms of sine. So I just wanted to show you that sometimes we do have to work backwards, because once we do, we can realize that 2 things can apparently cancel out. So essentially what I did over here, I just rewrote this down here, and I just applied the formula to this integral. And the reason I did that was because now I see that this integral and this integral, they cancel out. And now we're just left with negative log of 2, and then we have x 0 to pi over 2, and that is equal to negative pi over 2 log of 2. And that is our final answer. So this one was a little bit tricky because we needed to know our properties of logs. But that is it for today's video. Hopefully you guys understood a little bit about this formula, and that integrals are now a little bit easier to solve because this formula comes in handy a lot, especially with trigonometric functions. We just need to know our identities for sine pi over 2 minus x and cos pi over 2 minus x, and then you are well on your way to solving more complex integrals such as this one.